In today's lab, we will be using a pulley system to determine acceleration by using the CAPSTONE program. Firstly, we will determine a theoretical acceleration, then compare it to our experimental acceleration to find our percent error. Afterwards, we will combine another pulley to our system and repeat the entire process.
So for this lab, our materials are using this pulley system with 2 hangers, and then here are our weights, our universal interface, and then our capstone.
Hi guys, welcome. So this is going to be lab report number 7. We are team 3. So here's our table for that. So this is our theoretical acceleration. Our team went ahead and selected 70 grams for our first mass, and then 10 grams for our second one. And then yeah, we just basically input our values here and then multiplied it times our gravity, which went ahead and gave us a acceleration of 7.35 meters per second squared, which we put here. And then after we achieved that value, we went ahead and started our experiment development, at least for the first system. So for experiment, basically we ran this pulley system. So right here, we just explained our theoretical of what it should be theoretically. And then we went ahead and ran it ourselves on our own little system as shown previously in the videos. So here, basically, it's just explaining the same thing with the pulley system that we start the recording and then let the weights balance out due to gravity, or at least let the weights like interact with each other. And then we were to go ahead and catch it at the very end before it hit the floor, just so that we can get a precise graph. And so basically from the data that we got, we went ahead and took screenshots that I'll show you right now. And then with that, we went ahead and accurately able to get our experimental acceleration and our percent error. Yeah. Okay guys, so here's the graph for the very first pulley system. So basically here, we went ahead, after we calculated it, we went ahead and grabbed 2 points from the graph. Basics, simple stuff from like the slope and whatnot. And then we got these 2 values right here. And then we went ahead and put it into this equation, which I'll show you right now. And then just compared them to each other to go ahead and get our experimental acceleration. So from here, we're gonna go ahead and come here. Sorry, ignore that third table. But we went ahead and used this equation here, which is basically like delta V over delta T, which is the final minus the initial for both of them. And then we input those values that we found on that graph that I just previously showed you right now. And then we went ahead and got these values right here, 3.24 meters per second squared minus 1.1 meters per second. Or sorry, meters per second, not meter per second squared. And then divide that over this time. And then yeah, it basically gave us an experimental acceleration of 6.32 meters per second squared, which was, compared to our theoretical, a 14% error, which was pretty good. Well, I would say relatively good. Obviously, we're hoping for like a 0% error, but sometimes the systems can't be perfect, or there's a lot of things that have to go into consideration, which I'll go into detail later in our concluding points and our questions are, yeah. So basically afterwards, we finished with the very first system. So then we're gonna go ahead and move on to the 2 pulley system. So I'm just gonna go ahead and expand on that a little bit. So after we finish this, you know, after our multiple trials, we went ahead and moved on to our step 2, which is basically now a 2 pulley system. So same thing, but now we just have 2 pulleys instead of 1 with the weights. So now we select 2 new masses and they had to follow this they had to follow this rule right here, which is basically m1 minus 2 times m2 had to be more than or equal to 50 for our rule. And yeah, so then we went ahead and built this setup right here as shown in the second part of the video. To minimize the error and whatnot, we went ahead and made sure that it followed this rule for the inequality between the two masses and the system itself. So yeah, then now we went ahead and set the system up, and to determine our acceleration, at least theoretically for this third graph right here, we were going to go ahead and use this one, which is negative 2m minus m1 divided by 1/2 of m1 plus 2m times our constant gravity, which is, as previously shown, 9.8 meters per second squared. So then afterwards, we were able to get our theoretical acceleration, which we were going to put here. And I'm just going to go ahead and show that right now. So for our theoretical acceleration, my team and I went ahead and chose our mass, which followed the same rule, which is mass 1 has to be larger than mass 2, just so that it would be able to follow this rubric and obviously be able to give us like a good theoretical acceleration. So with that, we went ahead and chose those values right here. And then obviously this is the equation that I just showed right now. And then you just substitute all the values of the the masses of each weight. And then afterwards, it went ahead and gave us a value of 6.53 meters per second squared, which we went ahead and put in here for our theoretical acceleration. And then right here, just demonstrating the rule that we had to follow. Sorry, I misput this, but it was supposed to be 2 times m2. So then afterwards, it went ahead and gave us a mass of 60 grams, which followed our rule of it being larger or equal to 50. So after that, yeah, we're gonna go ahead and swap to our experimental graph. Okay guys, so here's gonna be the graph for the experimental for the 2 pulley system. So here are our values right here. Same thing, we got the slope of the system when it recorded with the sensor. And then we obviously, same thing, the delta V over delta T, we went ahead and grabbed the velocity over time for both of these points, subtracted them minus each other, and then went ahead and found those values. Okay, so then with this graph, then we're gonna go ahead and shift to our experimental acceleration here. So after we do our theoretical, then we obviously assemble the system, and yeah, so then we chose the exact same masses that we chose in our theoretical, and we went ahead and put them together, we went ahead and got the values that we did from the graph I just showed you right now, and we input them obviously into the acceleration, like the delta V over delta T, and it went ahead and gave us a value of 5.29 meters per second squared, which also gave us a percent error of 19%. So basically from the 2 experiments, we got pretty decent percent errors. Obviously, like I said, we would want it to be 0, but unfortunately there's some outside factors or maybe some difficulties on our end to be able to replicate it exactly, the theoretical that we wanted. So then we're gonna go ahead and hop over here. Obviously the graph, once we finish the graph, we go ahead and report it, which we just did right now. And then I'm basically just gonna go over some summarizing points and some conclusion and whatnot in today's lab. So we went ahead and skipped this step right here, but then we hop into step 5, which is considering the percent error with the motion sensor and whatnot. So basically just gonna go into depth about that a little bit. So it says, in considering the percent error are used to having with the motion sensor, was today's percent error greater or smaller, and why? So from the sensors that we've been dealing with over the semester and with the carts, I'm gonna go ahead and explain that a little bit or go into detail. So that's gonna be question number 1. So for today, in today's lab, we determined that the percent error for both experiments today were smaller, usually than when we do it with the carts. Obviously, with the sensors with the carts, it might be a little bit more difficult to be able to determine our values due to its setup and the sensor maybe having like a certain range before it becomes unregistered. So it may have been proven difficulty to be able to find a good percent error for the carts, but luckily for us today, it wasn't too difficult to find the percent error for the pulley systems. Now jumping into question 2, it says, between today's 2 setups, which one had more significant percent error? As described earlier, we said that between both setups, the experiment for the 2 pulley system proved to be more problematic with the percent error. And that was just due to a lot of testing, and obviously we have to deal with now there being more rules such as the 50 gram the 50 gram minimum, and then obviously having to deal with 2 pulleys instead of 1 pulley, which is a more complex system and whatnot. So with that, we determined that the second setup was a lot more difficult to have a larger significant percent error rather than the regular one, which gave us just a 14% instead of 19. Now jumping into the last question, it said, what other factors besides friction could contribute to your percent error? We put that besides friction being a factor, of course, other factors that could influence the percent error could have been the different weights of the system or the system itself. So obviously the different weights of the systems that we tried multiple different weights for each of the systems. And so it was just a lot of trial and error, which obviously is a large factor when contributing to our percent error and trying to determine like a good value that would give us a rather decent experiment result. And then obviously the system itself, as shown in the video, it's a good system, like it did run properly, but I think the more ideal setup would be somewhere like maybe against a wall or something a lot more stable than just like a stand setup. But obviously the system itself was proven to be very good when doing the experiment. It could have been a beneficiary to the reason why we got such a percent errors that we did. So yeah. And then now I'm just going to jump to the conclusion with all of these in mind. So during this experiment, there were multiple trials due to the introduction of the new system and different weights and whatnot. So it obviously took us a little bit to be able to fix everything and just get used to it. But our team was rather successful in being able to obtain a low, or what we believe a pretty decent percent error compared to our theoretical values. So thankfully for all that, we were able to complete the lab and went ahead and fill out all of our tables. And yeah, thank you so much. These are our credits here. So me, Alex, I went ahead and did the calculations and explanation of the lab. Sherilyn went ahead and helped with experimenting, or the experiment and recording. Nadine went ahead and helped out with recording and calibrations of our system. Sophia went ahead and helped us set up the system and also helped with recording and doing our introduction. And Ileana went ahead and helped us out with our experiment and doing calculations as well. Yeah, thanks so much.